Awesome. Well, so we can slowly get started. Welcome, everyone. Seems like hope it's all working now. And we got many people joining for the second phase of our study group. So, yeah, welcome everyone, not just to this call, but to the third week and the second part of our study group. The first 2 weeks were introductory, and now we are diving deeper into the protocol. Today we are starting a track on cryptography. Are going to have 5 lessons on math and cryptography behind Ethereum. To understand the cryptography, really, it has certain requirements of knowledge of math, algebra, and we shared some pre-reading here. Actually, what Matan already wrote here. Let me share the book here as well. This is the link to the reading material. So this course is composed based on the Matan's teachings from the past courses, this whole book project. So you can always find the resources and take your own pace when reading this book. And yeah, it's my great pleasure to welcome you here, Matan, our teacher, our professor here. Matan is a PhD in mathematics, studied in Israel, in Netherlands, in Germany, active in multiple fields and a part of Ethereum Foundation's the PSE team. Also did the where he also did the whole course that I shared with you before, guys. But for us, he prepared a special version where he condenses it into 5 sessions. So it's gonna be intense. I hope you guys are ready to do some real math. And yeah, Matan, I mean, the stage is yours. It's your class basically. But if you guys need anything and if you have any questions, we are still here for you. So yeah, thank you so much for joining us.
Thank you, Mario, for the kind introduction. And hello, everyone. So, as Mario said, I'm um, I'm a mathematician by training. That's what I did my most of my adult life in academia. But since a few years, I'm out of academia and working in various places. Currently at Ethereum. And one of the things I do is try to teach mathematics for cryptography for people without a formal background, let's say, apart from high school.
Yeah, sorry about the noise.
And as part of the sessions that we planned with Mario, the idea is to give you a taste of the mathematics that is relevant for cryptography. If you look at the book, you see that the book is much longer than anything we can hope to cover. But still, we can sketch a few things. And apart from the mathematics, of course, we will discuss some cryptography that is built on that mathematics. Somehow my tablet is okay. It's sharing.
Yeah, it's all here.
Um, so today I want to talk about hopefully two things: groups and fields. Each one of these topics is, in fact, in the university, you take it as a semester, a course for an entire semester, one on groups and one on fields. So obviously, we're covering a very surface level things. And nevertheless, I think it's actually a nice challenge for me to try to find the shortcut way of teaching you what is really needed in cryptography and getting to actual applications. Okay, and I asked Mario to circulate a prerequisites that is, I think, chapter 1 or 0 in the book, which is sets and functions. But let me do a recollection. So a set is a collection of elements, and that is written with curly brackets, and each element, I mean, the elements are separated by a comma. So, for example, you can write the set A as 3 elements, 1, 2, and 3, and you see the curly brackets in the left and right hand sides, and comma separating elements. Another way you can write a set is by, let's say, B is the set 1, 2, 3, dot, dot, dot. So this dot, dot, dot really means that there is a rule that is transparent from the first few elements, and the set contains all the elements that satisfy the rule. So this set of elements is the natural numbers. This is natural numbers. In fact, usually it is denoted as this fancy n. And another way to specify a set is again with this rule, but instead of doing these 3 dots, I can do, let's say, B is the set of all x's such that x is a natural number and x is bigger than 5. Okay, that's also a legitimate set, and this is a convenient way to do. This is like the entry condition to the set, and this line is all the elements satisfying the entry condition. One thing I forgot to say before I move on is that I like questions. I think generally questions are helpful both to you and to me. And I don't want to restrict the questions only to the end of the session. So feel free to raise a hand and ask whenever you want. And with that said, we will also do, I forgot to say, but the plan for today and for the other sessions is to do 50 minutes first part, and then a 10 minutes break, and then an hour for the second part. We will, of course, reserve some time for questions at the end, but again, feel free to ask during the sessions. Okay, so if I can write a set like with this entry condition, then I can define the following set. This is the empty set. It's the set of all x's such that x is not equal to x. Okay, so you see that this kind of interface it gives me flexibility to write a pretty complex logical entry conditions that define sets. And of course, the empty set is important for many kind of anchor applications. One thing you can do with two sets is to take the Cartesian product of sets A and B, is the set that is denoted A x or A times B, and this is the set of all ordered pairs A comma B such that A is an element in A and B is an element in B. This thing. And so, for example, if you take A to be the interval 1 up to 2, so this is on the line of numbers, this is the set of all numbers between 1 and 2. And you can take B to be, let's say, the interval 3, 4. This is let's say this. And then the Cartesian product of A and B will be a subset of the two-dimensional plane that is depicted as follows. So let's say this is 3 and this is 4. And then you take the square like so, is in fact the Cartesian product of A and B. Okay, and last but not least, from the recollection is what is a function? So a function f from A to B is a rule that assigns for every element A in a unique element B in B, denoted f of A. And so you can think of a function as like a computer program in a typed language. That is, this is the input. This is A is the type of the input. B is the type of the output. And a function is like a function in a typed programming language that has the input type A and the output type B. So it is it needs to give you a way to associate a unique output for any input.
We have a question in the chat, Maten, asking, true random cannot be a function, correct?
Well, what is true random? There is a section in the first chapter of the book about the Cantor theorem, and one of the corollaries is that true random cannot exist. So that may be some answer. But again, you can try to define true random in a different way, and then the discussion becomes more involved.
Great, thanks. Did that answer your question, Hamid?
Okay, so if a function is like a program, we should also be able to compose. So if I forgot to say the notation for the function, right here in yellow, you write f colon from A to B. And of course, if I just change the output set B to some B prime, then it's considered a different function, even though the elements in B prime that do not exist in B may not be achieved by any input. So it's like in a typed language. If you declare the function to be to have an output type B prime, then it is by definition it's different than a function with an output type B. And so given two functions, f from A to B and g from B to C, then I can compose g composed f is a function from A to C given by a g composed f applied on an input A is g applied on f applied on an input A. Okay, so this is the reason for the order g and then f. Okay, so that's the preliminaries. And we are set to talk about groups. So let's give the first definition. A group is a set G with binary operation let me call it for now star from the Cartesian product of G with itself to G. And that is, you take two elements, X and Y, you apply this star, and we will write X star Y for short in what follows. Apart from the binary operation, we require to have a specified element E in G such that the following conditions hold. So the first condition is, let's call it unitarity. This means that for any X in G, X operation E is equal to X, and it is also equal to E operation X. Two is usually called associativity. that for any x, y, and z in G, if you do, I mean, we have a binary operation, so you can only do x operation y, or y operation z, or x operation z, and then take the result and do operation with z. But you can also, a priori, you can also do y operation z and take the result and do operation with x. And as the associativity axiom requires that these two things are equal. And what associativity gives you is it tells you that whenever you have a long string, you know, A1 operation, A2 operation, AN, you can write it, in fact, without brackets, because any bracketing of this of any finite expression with the binary operation is going to be the same by the associativity axiom. And the third axiom is invertibility. And this says that for any x in G, there exists some element y in G such that x operation y is equal to E and is also equal to y operation x. And we denote x minus 1 to be this y. So this is typically, it's like imagine that this operation start with multiplication of numbers, then x to the minus 1 would be the inverse. I mean, would be the number such that x times x minus 1 gives you 1, which is the neutral element. This this element, by the way, is called neutral. So it's neutral because of the unitary axiom, right? You do the operation of x with the neutral element, you always get x. Okay, so this is a group, and of course we want to have examples. So some famous groups. One is you take the integers. This is denoted as z, and you take the binary operation to be plus, and the neutral element to be 0. This is a group. The inverse, what is the inverse of an element A in Z? The inverse is going to be minus A. So A minus 1 in this case is going to be minus A. Now, if you want something with multiplication, you can take the real numbers, remove the 0 element, and take multiplication and the element 1 as the neutral element. This is another group. And this time, if you have an element A, then A minus 1 is really just 1 over A. And now let's take an example that comes a lot in cryptography. This is integers modulo n. So integers modulo n is all the possible reminders of doing long division of an integer by n. What are all the possible reminders? It's 0 up to n minus 1. And I need to do, I need to give you the binary operation. So the binary operation here is denoted modulo plus modulo n. Maybe we'll put it, the mod n as a subscript. And the neutral element is 0. So what I mean here, if n is equal to 12, then this is what you know as clock arithmetic. That is, if the time now is 11, and I ask you what will be the time 2 hours from now, then you do 11 plus 2, that's 13, and then you do long division by 12, and you take the remainder of what you have left. This is 1. So 2 hours from 11 is 1. And that is exactly what I mean by plus modulo n. So 11 plus 2 modulo 12 is 1. So 11 plus 2 mod 12 is equal, we write it like this, equal to 1. Okay, and so we still need to verify that we have the inverse for every element, but that's easy. If you give me an element k, then I also have the element n minus k, and k plus n minus k is equal to n, and n is equal to 0 modulo n. So k minus 1 is n minus k. And now the fourth example, something a bit more geometric. You take a perfect triangle, you denote vertices by say 1, 2, and 3, and now you take all the symmetries, so symmetries of let's say T, you can regard the symmetries as functions on vertices. That is, one symmetry is a reflection. So I take a reflection's axis like so, and that would mean that 1, 2, 3 is mapped to, so 1 is not affected by the reflection along this axis, so 1 stays 1, but 2 becomes 3, and 3 becomes 2. So this is one reflection. This is one symmetry. You can do 2 other symmetries in the 2 other axes of symmetry, and you also have rotations, 3 rotations. So say the rotation like so. So this would be 1, 2, 3 goes to 2, 3, 1. Okay, so we have in fact 3 reflections. and 3 rotations. And what is the binary operation? I mean, these are functions. So the binary operation is simply composition of functions. Or if you wish, it's like, you did one symmetry. Let's say you did a reflection, and then you did another symmetry, say a rotation. You simply do one and follow it by the other. And of course, every element has an inverse because, well, for example, the rotation I described has an inverse if you do the rotation in the other direction. And the reflections also have inverse if you check it. So this becomes a group. The neutral element, of course, is the operation that doesn't do anything to the vertices. So 1, 2, 3 stays 1, 2, 3. It is usually called the identity. So this is a D3, the dihedral group, and a D3 has 6 elements. Okay, so we now want to restrict, you see, this example 4 tells you that groups can get...
Excuse me, somebody has a mic. Okay. Sorry, brother. You can go on.
So this a fourth example is meant to show you that groups in general have a very... Yes. What was the question? Why D3 has six elements? So how many reflections do I have? I remember, it's like we only consider perfect symmetries of the perfect triangle. So the reflections, you have to choose a reflection axis out of the 3 options I described here. And rotations, you can either do the rotation I did, 1 moves to 2, 2 moves to 3, and 3 moves to 1. This is you can regard it as the trivial rotation. So it's like I don't do anything, and I can do 1 goes to 3, and 3 goes to 2, and 2 goes to 1. Okay, so that's the third rotation. So all in all, I have 3 reflections and 3 rotations, and that's 6 elements. But the point is, you can read about it in the Wikipedia or whatever. It's just to show you that the structure of groups in general can be very, very complex. But we are going to make a simplifying assumption. A group is abelian. Let's say a group G is abelian if for any x and y in G, x operation y is equal to y operation x. And if you look at it, examples 1 up to 3 are abelian, but example 4 is not abelian. And I leave it as an exercise. You find 2 elements, x and y, in D3, such that they don't commute. Okay, so henceforth, all groups are a billion. Still, there is a notational discrepancy. You can, I mean, I describe the group by G star E, and let's say the inverse operation was -1. But you could describe a group with the binary operation being plus, and then it is most natural to call the neutral element 0. And the inverse, you do minus the element, right? This is like you know from numbers. And on the other hand, sometimes, I mean, you may want to write the group G with a multiplicative binary operation. And then it's more natural to call the unit element, the neutral element, 1. And the inverse operation you keep as -1. And let's say both these two notations are useful, because sometimes, as you saw in the example, sometimes the structure I get from the group, I mean, I get the group intuitively. It's very easy to think about it in terms of addition, and sometimes it's more natural to think about it in terms of multiplication. So I can interchange these two notations. Now, if G written multiplicatively is a group, a subset H inside G is a subgroup if the following conditions are satisfied. One is that the neutral element 1G belongs to H. And two, for any x, y in H, x operation G with y belongs to H. So this is a certain closeness of the subset H. And the third axiom is for any x in G, for any x in H, if you take the inverse of x with respect to the binary operation of G, then this inverse element still belongs to H. Okay, so in other words, H with the operation of G restricted to H is a group in its own right. So, for example, you can take and I forgot to say the notation is H less equal than G. This is when H is a subgroup of G, we denote it like so. And classical examples, I mean, you take the integers. This is a subgroup of the real numbers. The real numbers, if you take the real numbers with addition, of course. Another example is you take integers modulo 10 and you take the subset 0, 5. That this subset is in fact a subgroup. But if you take the subset 0, 4, this is not a subgroup of integers modulo 10. Why? Because if I do 4 plus 4, using the operation in integers modulo 10, my operation is plus modulo 10. So since 4 plus 4 is equal to 8 modulo 10, and 8 does not belong to 0, 4. Okay, so I don't have the subset H is not closed under the operation of the ambient group integers modulo 10. Another non-example, anti-example, is integers modulo n is not a subgroup of the integers, even though it is a subset. Integers modulo n, I remind you, it's like the set 0 up to n minus 1. And so obviously it's a subset. It's a subset of the integers, but it is not a subgroup because the operation in integers modulo n is not the same as the operation in integers. In integers, I do simply addition, and in integers modulo n, I do addition modulo n. It's completely different. Okay, so so don't be fooled by there are many cases in which you have a subset of a group, but this subset is not a subgroup because the operation on the subset is not the one coming from the ambient group that you started with. So now the following theory: if G a finite group is a finite group, and H is a subgroup of G, then the number of elements of H divides the number of elements in G. This is divides. Okay, this is Lagrange theorem. And you can see that in the example we gave, 0, 5 is a subgroup of size 2, and indeed 2 divides 10. Using Lagrange theorem, you can start think about what are all the possible subgroups of a given finite group, right? Because there are not many divisors, usually not many divisors of small integers. And that is computationally feasible many times to simply classify all the subgroups. And Lagrange theorem is helpful in that regard. So as an exercise, I propose size, write all subgroups of integers modulo 20. Okay. Now,
there is a question in the chat asking, how can there be an infinite group?
Yes, so infinite group, the integers, for example, is an infinite group, right? Infinite simply means that the number of elements in the set of the group is not finite. So yeah, integers, or you can take the integers Cartesian product with the integers. And then I saw also somebody ask what is divide. So this is a positive, this is a positive integer, say n, and this is another positive integer, say k. And we say that k divides n if I can write n as k times l for some l. There exists some l such that k is n is equal to k times l. Any other questions before I move on?
Feel free to ask, folks, to make sure you understand. It's no shame to have questions. You can also raise your hand, and otherwise we can continue. Yeah.
Yes. So the next thing, and this is a central concept of groups that appear in cryptography, is the following: a finite group G, let's say written multiplicatively, is cyclic if well, let's say the number of elements in G, I'm going to denote it by n, and I call such a group cyclic if there exists G in G called generator, such that the entire set big G can be written as a G to the 0, which is 1, G square, up to G to the n minus 1. Okay, so this it sounds maybe surprising that there are such groups, but in fact, they appear quite often, and in some sense, they are the building blocks of a finite abelian groups. So in basically every finite abelian group can be can be described as the Cartesian product of cyclic groups. But for now, it looks special. I should warn you. Such G is not necessarily unique. Right, so a group is cyclic if it has a generator, but it can have more than one generator. Now, of course, I wrote the definition in a multiplicative way. If G is written additively, then G is cyclic if there exists some G in G such that G is equal to 0, which is G plus G, up to G plus G plus G and n minus 1 times. And that's it. So this is I'm simply translating the previous definition to the additive notation. And in both cases, we write G triangular brackets small g. This means that the group G is generated by the small element, by the element small g. Now, examples. Of course, you can take, say, G is equal to integers modulo 6, and it is generated by the element 1, because you do 1 plus 1 is 2, 1 plus 1 plus 1 is 3, and so on. You get all the elements. But also, this is slightly less obvious, Z mod 6 is generated by the element 5. Why? You take, well, I'll leave it as an exercise. And in general, integers modulo n is generated by k if and only if k is what is called coprime. So it does not have any common divider to n. Now, I don't have to have Z mod 6. I can have Z mod 3 times Z mod 2. This is also cyclic. I claim that this is generated by the element 1 plus 1. How come? Well, I write all the sums of 1 plus 1 with itself. So 1 plus 1, 0 times, the 0 sums with itself is 0. And then 1 plus 1 comma 1. 1 comma 1 plus 1 comma 1. Remember, in the Cartesian product of two groups, the binary operation is coordinate wise. So the binary operation in integers modulo 3 times integers modulo 2 is, I mean, if I do 1 plus 1 comma 1 plus 1 comma 1, I need to do in the first coordinate 1 plus 1 modulo 3. So this is 2. And in the second coordinate, I do 1 plus 1 modulo 2, but that's 0. And then, so this is 2 times 1 comma 1. And if you do the calculation of 3 times 1 comma 1, you get 0 comma 1. 4 times 1 comma 1 is going to be 1 comma 0. And a 5 times 1 comma 1, that is, you add 1 comma 1 to itself 5 times, you get 2 comma 1. And you see we covered all the options. This is 6 options, all generated by sums of this element 1 comma 1 with itself. So okay, so we have some other possibilities of cyclic groups. And I guess we're almost in time for the break, so let me state the fundamental theorem for cyclic groups. So let G written multiplicatively be a finite cyclic group. Then one, every subgroup H of G is cyclic. And two, if the number of elements in G is n, and let's say G is generated by small g, then G, so you take the group generated by G to the n over k, well then for any k that divides n, if you take all the powers of this element G, small g, the generator, to the power of n divided by k, this is the unique cyclic subgroup of G of size k. Okay, so now you can use the fundamental theorem of cyclic groups to classify all the subgroups of integers modulo n. Okay, using a generator, using other means, if you will. And okay, let me stop here. But of course, I'm happy to take questions before we take, let's say, a 10 minutes break.
Yes, we had some questions. First was about the exercise. Maybe if you can share a solution to that, because Alank wasn't sure how he can be sure that he wrote all the subgroups.
Of what?
That was even more up, I think, the exercise before.
All the subgroups of integers modulo
Yes,
20.
yes.
Well, okay, try int. First of all, you can find it in Google, but you can try integers modulo 10 if you want. That's you know by Lagrange theorem that the size of a subgroup has to divide the size of the group. You only have two divisors here for 10. Again, I would recommend just Google it. I'm not going to write things that can be easily found on the internet.
Yeah, that's fair. That's fair. Yeah, thank you so much. And there was a question about the current part about whether the definition allows to so the groups can be defined multiplicatively or additively, but we would want to both add them and multiply, right? Do the definitions we've seen allow for both at the same time?
I don't understand the question. I
Feel
sorry.
free to raise your hand or maybe refine your question, and we will have a pause soon, and you can maybe prepare questions during the few minutes break.
So groups can be defined multiplicatively or additively, but we would want to both add and multiply. So it's not like we would want to both multiply and add. It depends on the context. So a group is like a collection of elements with a binary operation satisfying some conditions. Now, many times, especially in cryptography, this collection of elements is a collection of numbers. But numbers we can both multiply and add. And sometimes the binary operation is going to be some kind of addition, maybe addition modulo n, and sometimes it would be some kind of multiplication, like a multiplication modulo n, or multiplication together with some other things. But it can also be something completely, it can be some kind of weird formula that involves both addition and multiplication. Then maybe the better notation is to just do the binary operation, write it as this star asterisk that I said, and this, and regard it as an abstract binary operation. It eats two things, and it spits out a new thing. What is restricted? So when I said that a subgroup, this is, I mean, where did I define a subgroup? Yeah, so here, restricted. When I said a subgroup is like a group when this operation dot g is restricted to age. It means, I mean, you have a binary operation that is a function from g times g to g. This is dot g. But age is a subgroup, so age times age is also age is a subset, so age times age is also a subset of g. So you can take the function and it's like define it on a smaller input set. This is age times age. This is restricted. So age is given that age is a subset, this age is a subgroup if when you restrict the binary operation dot g to age, so this is usually written dot g in this line, age times age, and then you get, I mean, a priori you get something to g, but in fact we demand it to be something in age, and so this needs to be a group. But maybe I shouldn't have complicated the definition in this way. So you can just ignore this part. There is a perfectly good definition of what is a subgroup here. Yeah, okay. So let's take a 10 minutes break now. And of course, you can write more questions meanwhile, and we resume. So let me, so I don't see any questions, but of course you can ask later. The next thing I want to talk about is a very central notion in mathematics in general, but it's also important for us. I mean, and this is called isomorphisms. We saw that, well, let's say integers modulo 6 is, well, it's a group of size 6 generated by one element. And also, integers modulo 3, Cartesian product with integers modulo 2 is another cyclic group of size 6 generated by another element, which in this case is different. It's 1, 1. And let me scroll back. You see, in integers modulo 3 times integers modulo 2, we can denote this guy, we can denote as 0, this as 1. This is 1 plus 1, so we denote it as 2, 3, 4, and 5. So under this change of notation, we have essentially integers modulo 6. I mean, if you look at the binary operation can be defined by a finite table. You put, it's like a addition table, right? You put all the elements 0 up to 5 in a row and in a column, and you do the addition table. The addition table of integers modulo 6 will be identical to the addition table of integers modulo 3 times integers modulo 2 under this green change of notation. And so we would like to say that these two groups are in fact the same, but they are not, obviously they are not the same on the nose. They like, one has 2 coordinates and the other has the 1 coordinate. It's so we want a notion that says that these two, that two groups are the same up to, let's say, a change of notation. And this is isomorphism. But before, so I need to say what is what does it mean to have a complete a change of notation? And this is the following notion. A function of finite sets, let's say f from A to B, is a bijection if 2 conditions are met. One is that for any 2 distinct elements, A1 and A2 in A, f of A1 is different than f of A2. So it's like f has no repetitions. And 2, for any possible output B in the output set big B, there exists an input A in A such that f of A is equal to B. By the way, this condition 1 is called injective, and condition 2 is called surjective. So, for example, if I give you A and B like so, and I have it, I have the function described as the arrows here, then this function is injective. This is injective. It satisfies condition 1. For any 2 elements, A1 and A2, or A1 and A3, and so on, you apply the function and you get 2 distinct elements in B. And surjective is, let's say I have 2 elements here, I may have 3 elements here, then I can send the elements like so. And this is surjective. And bijective, so you see, injective, in fact, really implies that the size of the set A has to be smaller or equal than the size of the set B. And surjective implies that the size of the set B has to be smaller or equal than the size of the set A. Because surjective is like a covering, and injective is like an embedding. Okay, and bijective is both a surjective and injective, so it's both an embedding and a covering. It means this is a theorem, but it's actually very easy. So let's say observation. The size of A is equal to the size of B if and only if there exists a bijective map, bijective function, f from A to B or f from B to A, doesn't matter. Okay, so that's what we mean by let's say a one-to-one correspondence, a change of names that does not omit any of the names in the domain set and does not omit any of the names in the range set. So now what do we do for groups? So let's say G is a group written multiplicatively, and H another one. An isomorphism from a G to H is a bijective function f from G to H such that the following conditions are met. One is that f takes the neutral element in G to the neutral element in H. Two, for any two elements in G, if you apply f on the multiplication of x and y in G, then it's the same as applying f on x, applying f on y, and taking the multiplication in H. And three, this follows from the previous two. For any x in G, if you apply f on the inverse of x, then you get the same as applying f on x and taking inverse in the group G. Now, so this is an isomorphism. And what is happening here? Let's say G is three elements, A1, A2, A3. One of them is the unit element, but I don't care. And write H to be f of A1, f of A2, and f of A3. Why can I do it? Well, since there is an isomorphism from G to H, then the number of elements in G and in H as sets has to be the same. And since f is injective, if I apply f on A1, A2, and A3, I get three different things. And since H only has three things, I get all the things in H. So this thing here is, if you will, some particular enumeration of the elements in H. Okay, and now I write the multiplication table of G. Say A1, A2, A3, A1, A1, A2, A3. Here I have A1, 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 A2, A1, A3, A2, A1, A2, 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 A3, A3, A1, A3, A2, A3, A3. Now I do the same, but for the multiplication table of age using this particular enumeration that I chose. So I have f of A1, f of A2, f of A3, f of A1, A2, f of A3, and multiplication in age. So here I have f of A1 times f of A1. And here, well, I'm not going to write all of that, but let's say here is going to be f of A2 times f of A3. Now look at what is going on. F is an isomorphism. So I go back to the definition. I see that condition 2 says that if I apply f on multiplication of two elements, it's like applying f on each of the elements separately and taking multiplication in H. So what I have here is in fact by condition 2 is equal to f of A2 times A3. And this, again by condition 2, is f of A1 times A1. So you see, what I have here is this element A1 times f A1 was simply mapped to f of A1 times A1. This is the first element in the multiplication table of H. And this element was mapped to this element. So you see, I using this enumeration, F is simply a complete identification of the two multiplication tables of F, of G and of H. So in fact, G and H are the same up to a change of notation. What is the change of notation? Just apply F on the elements of G. In other words, in a computer representation of G or H, the computer doesn't care. H and G are the same. And that is the example we had of integers modulo 6 and integers modulo 3 times integers modulo 2. It's these two groups are isomorphic. And so from a computer point of view, it's the same. So e.g., the notation, by the way, Z mod 6, isomorphism is like equality with the tilde over it. So Z mod 6 is isomorphic to Z mod 3 times Z mod 2. Remark. And not every, so we are dealing with stuff that are need to be also computationally feasible. Sometimes the two groups are isomorphic, but it's not easy to find the isomorphism. It's in fact, in some cases, it is considered computationally infeasible to find a certain isomorphism between two groups. So not always computationally feasible. Okay, so now that we have this notion of isomorphism, here's a theory. If G is a finite cyclic group, G is isomorphic to integers modulo n, where, of course, n is simply the number of elements in G. Okay. By the way, how do you define this? This theorem is very easy to prove. Let's say you have G written additively, and you know that G is cyclic, so it is generated by some guy G. You simply define a function f from G to Z mod n by saying that G goes to 1. And of course, G plus G would go to 2, and so on. So you see, so in fact, up to isomorphism, all finite cyclic groups are isomorphic to some integers modulo n. This is the importance of integers modulo n. But as I said earlier, it is not always computationally feasible to find such an isomorphism. And now we arrive for the main theorem in the theory of finite abelian groups. This is a structure theorem for finite abelian groups. If G is finite abelian, then there exist positive integers n1 up to nk such that G is isomorphic to integers modulo n1 times integers modulo nk. Okay, so this concludes the the very short mini course on groups that I wanted to talk about. Any questions before we move on to fields? How to prove what? The structure theorem. The structure theorem. This appears in the notes, but this is it's not something I can answer easily. I mean, it takes some time. So if you want the full the book I wrote contains full proofs for 95% of the things on up to elliptic curves and pairings. So if you have the patience, I recommend, but I cannot really answer, and we cannot really cover it in these sessions. Why must be abelian groups? What is the questions? What is the question here, Lee? It's yes. Go ahead.
Yeah, in the final theory, we have like we define this theorem for abelian group. So I'm wondering if that also could be extended to other type of groups, or it only applies to abelian group.
So this is only applicable for abelian groups. However, and as I said, the proof of this appears in the book I wrote, but of course it's not my proof. It's well known. So in a few pages of the book, you can find all the details. If you want a structure theorem for all finite groups, not necessarily abelian, this is a much more complicated question, but it was answered. This was a huge project of mathematicians in the second half of the 20th century. And the classification, it is a theorem, if you will, that takes about 10,000 pages. So you see, when you move from abelian to non-abelian, the mathematics become much more complicated. There is still a classification theorem, but it's very hard. So we take a huge simplification here. Yes. Okay. So we have 17 more minutes, and in this time, I would like to start talking about fields. We will continue next time. So if you looked at the titles of the sessions, the next session should be on fast Fourier transform. What I plan to do, the titles are kind of tentative because it's not clear. It wasn't clear to me how much I would be able to cover in the given time frame. But I think what we'll do is we'll talk about fields today. We'll talk about fields next time as well. And we'll probably next time we'll start talking about fast Fourier transform, which is a very good, in my opinion, a very good application of the stuff we talked about in the groups and fields session. So what is a field? A field is a set F with two binary operations. Usually one denotes them as plus and multiplication. Together with two elements, these are like special elements, 0f and 1f. Satisfying the following axioms. One is that both f with plus and 0 and f when you remove 0 and you take the multiplication and the element 1 are abelian groups. And 2, for any x, y, and z in F, x times y plus z is equal to x times y plus x times z. So you see, what does it mean that F with plus and 0 is an abelian group? It means that for any element x in F, I have an element minus x such that x plus minus x is 0. And what does it mean that F removed, when you remove 0 with multiplication and 1 is an abelian group? It means, well, I mean, of course, abelian means that the plus and the multiplication operation are commutative, but it also means that for any x in F, there is an element x minus 1 such that if you multiply x with x minus 1, you get 1. Okay, so these are two operations. Both of them need to be need to satisfy the axioms of abelian group separately. So also associativity, right? If you do x times y times z like this, it needs to be equal to x, y, z like this. And the same for the plus, x plus y plus z needs to be equal to x plus y plus z with these brackets. Okay, and so on. 0 needs to be the neutral element with respect to addition, 1 the neutral element with respect to multiplication. And so this is spelling out what axiom 1 means. Axiom 2 is about the compatibility of addition with multiplication. This is called distributivity. Okay, so what are famous fields? One is the real numbers. The real numbers with addition, multiplication, 0, 1. 2, the complex numbers. 3, what is called the rational numbers. This is the set of all quotients a over b such that a and b are integers and b is non-zero. Observe. If I have a field and I have two elements in the field such that x times y is equal to 0, then we must have x equal to 0 or y equal to 0, or both. And the reason is that, well, if x times y is equal to 0, then I can multiply by x, and x is not 0. I mean, if by towards contradiction x is not 0, then I can multiply. I mean, there is x x minus 1, and I can multiply this equation by x minus 1. I get x minus 1 times x times y equals to 0 times x minus 1. And it's the same as saying y, because x minus 1 times x is 1, y is equal to 0. So if x is not 0, I automatically get that y is equal to 0, and vice versa. So now consider integers modulo n with addition modulo n, multiplication modulo n, and 0 and 1. And the question is this a field? So theorem, Zn is a field if and only if n equals p is a prime. Is prime. And how do we see this? So look, the associativity and inverse with respect to addition, and I mean all the axioms are pretty obvious. The only thing that is not obvious is a multiplicative inverse. So only thing in doubt is a multiplicative inverse. What does it mean, multiplicative inverse? I give you a number between 0 and n minus 1, and you need to find a number such that if I multiply my original number with this new number, and I do modulo n, I get 1. Is this inverse, or I mean, does this multiplicative inverse exist for all non-zero elements in Z modulo n? So if n is not prime, let's say n is equal to k times L, with k and L smaller than n. Smaller than n and bigger or equal to 1. In fact, bigger than 1. So this is not prime. Then k and L are zero divisors. I mean, k times L is equal, k and L are elements in integers modulo n, and k times L is equal to n, which is equal to 0 modulo n. And this is a contradiction, because in a field, remember the observation, in a field, if x times y is equal to 0, then either x is equal to 0 or y is equal to 0. And here we have that k and L are non-zero. So if n is not prime, any decomposition of L as a product of two numbers shows that Z mod n cannot be a field. Now, conversely, if n equals to p is prime, then now I want to show that there is a multiplicative inverse. So I take any non-zero number, k, in integers modulo p, which is integers modulo n, when I remove 0. Because P is prime, the GCD, the greatest common divisor of K and P, is equal to 1. I mean, they have no number that divides both of them. K is smaller than P, and P is prime, so they can have no common integer that divides both of them. By the extended Euclidean algorithm, this is in the book, there exist U and V, some integers, such that Ku plus PV is equal to 1, i.e. K times U is equal to 1 modulo P, because if I do modulo P, I remove this PV. So K inverse can be taken as U. U modulo P is going to be K inverse. Okay, and hence Z modulo P is a field. I mean, you can check the other axioms. They are very easy to check. Associativity, the only non-trivial axiom to check is invertibility with respect to multiplication. This is what the proof covers. So the notation FP is this integers modulo P with addition modulo P, multiplication modulo P, 0 and 1. This is the field, prime field. Okay, let me stop here, and we can take a few more questions before we end. Yeah, well, cryptography experts, feel free to push it further. You are welcome to ask here an abstract question. What is the connection or relationship between polynomials and sets in ZK proofs? I'm not sure what you mean, because set, as I talked about, a set is anything is a set, you know. Also, a function is a set. It's going to be a subset of some Cartesian product. So I'm not sure what, but polynomials. We will talk next time. We will definitely talk about polynomials. These are very central objects, and they appear everywhere. It's not just about ZK proofs. And maybe one of the messages of these lectures is, I mean, sure, it's good to learn about ZK proofs, but the mathematics apply to a much wider set of